Hi. Continuing from the earlier Laplacian transform video, let us look at a few other aspects related to Laplacian transform. So if you look at a unit step function, the idea is pretty simple that we have a, a function wherein before a certain value, it assumes a value of 0, and after a certain value, it attains a constant value and stays on that value for a long time. So if you look at a typical step function, it should look something like this, wherein, as I said, that we have no input or no value before a certain variable value, say a, right? So from 0 to a, the value is going to be 0. And a onwards, the function is going to attain some value. Now, this function, as you must have seen in the animation that I had shown in the previous video, may start at the origin, may start a little later, may start earlier in the sense before 0 or after 0. So that means we are shifting the function, right? And not to mention that we can use this for the inverse transform part as well, which is previously we have not yet thought about it, or which is not possible. So if you look at a typical unit step function, we would be writing as unit u of t minus a, wherein, as I said, it would be 0 before a and 1 after uh, you know t attains the value of a. It is that simple. So just like you going out and switching on the fan. So before you had pressed the on button, the fan was off, and when you pressed the on button, the fan started working. There was an input similar to that. So let us look at a typical function f of t. Say f of t is equal to 8 before below 2 and 6 when t is greater than or equal to 2, right? Now we are tasked to express this as a unit function and find its Laplace transform. So there's a very simple thing to do: express both the functions either in terms of 6 or 8. In this case, it is more convenient to express it in terms of 8. We do that, and then we further simplify it by taking out the minus 2 part as well outside. So we would have 8 minus 2 into, all right, because we will then divide it and multiply by minus 2, and that is how minus 2 comes outside. And then we would be simply looking at 8 minus 2u t minus 2, right? So this is the unit step function. This is how you do it. How to find its Laplace transform? It's very straightforward. Laplace transform of f of t, we know how, the property of linearity, so we can apply it over our function. So 8 into Laplace transform of 1 minus 2 into Laplace transform of ut minus 2. The Laplace transform of 1 is simply 1 by s, and the Laplace transform of ut minus 2, right? So in second shifting theorem, the idea is that if you have a function, say f of t, we know that its Laplace transform is f of s. So if you shift the function f of t and also include another function, how does that cumulatively work out? It is all about that. So say we have a function t square, we multiply that by ut minus 3, right? What about this? So t square into ut minus 3, what I do is I simply apply the principle that we had just looked at, meaning the second shifting theorem. So here I would write t minus 3 square plus 60 minus 3 plus 9. All right, and this would be ut minus 3. The idea is that somehow I want to convert the earlier function and the latter function's variable similar. So if ut minus 3 is the function, I would want to write t square somehow in terms of t minus 3. And I do this, numerical maneuver to attain that particular scenario. So if you look at now the equation, so Laplace transform of t square ut minus 3, and I get three, sub functions which or whose Laplace transform I need to find now. All right. Now, so let us again look at this individually. So Laplace transform of t square into ut minus 3. This is what we are intending to find. I have done all the calculations beforehand. You can do it individually, and this is what you should get at the end. Right? So it is that simple. So in principle, now you know how do you get this. So please let me know, if you are able to do all the steps. If you find any difficulties, please comment, and accordingly, probably we can have some discussion over there. Now, for assignment, I expect you that you can, try and solve these problems. One is t into ut of 2, then sine t ut of minus 4. And, they will be very interesting applications for the second shifting theorem. All right. Now, so let us talk about the impulse function. So if you remember just a couple of seconds earlier, what we discussed was very close to impulse function. First, we talked about the unit step function. Then we truncated the unit step function and brought down the output. Now, the same function, right, or the same relation I would want to use in my impulse function. Now, how do I write this? At A, I write t is equal to A. At B, I write t is equal to A plus 1 upon epsilon. And 1 upon epsilon represents a very, very small value. So impulse function basically would be similar to you hitting a nail with a hammer. The hammer and nail don't stay in contact for a very large period of time. They are in contact for a very small period of time, and a very large force is impacted on the nail. So when a large force acts for a short period of time, right, the product of that force and the time is called impulse. And in this case, it would be pointed out, I mean, the impulse function is a representative of that aspect. All right. So how do we write that? We write it as a simple delta, say t minus 1 is equal to 1 upon epsilon, where in what scenario? When the, variable lies in between a and a plus epsilon. Elsewhere, it is 0. So that is the idea. So if we talk about a unit impulse function, right, it would be delta t minus a. The values would be 0 to infinity, is infinity for t is equal to a, and 0 for t not equal to a. And when I say infinity, infinity meaning the, the spike would go on forever. And in the case of a unit impulse function, the spike would be a unit of 1 area, if you want to calculate. All right. So, and if you remember, I had shown this in this animation as well. Now, let us talk about the Laplace transform of unit impulse function. How do we calculate it? So let us write down the expression 0 to infinity f of t into delta t minus a dt. So I would write it as a 2a plus epsilon f of t 1 upon epsilon dt. And if we, simplify it or write it down, we can write something like this. We can introduce a new function eta, and simply, eventually, all you would get is a function in eta, right? And basically, what does that mean? So let me break it down again by using these two examples, right? So if we talk about 0 to epsilon f of t delta t minus a, right, we can write it as f of a, and f of t is equal to e raised to minus st. Say for instance, this is the case, this is the time function. Then I can write the Laplace transform of delta t minus a is equal to e raised to minus as simply. You can substitute and check for yourself. And there's another property by using which, or looking at which, you will be understanding this even better. Say for instance, we are looking at a function delta t minus a, delta dash t minus a, from minus infinity to plus infinity. So the answer then would be f dash a. Now, if you look at these two properties and say we apply it on a numerical, you would understand it even much better. So if you look at an integral minus infinity to infinity e raised to minus st delta t minus 2t dt, all right. So if we think about applying that, the formula that we had studied earlier, we can simply write e raised to minus 10, right? E raised to minus 10. Think about it. And if we think about using the second property that we studied about the impulse function, right? We can write, say for instance, t cube delta t minus 4. If we want to find the Laplace transform of this function, then we can write 0 to infinity e raised to minus st t cube delta t minus 4. And I can therefore, based on the principle that we had discussed earlier, we would get something like 4 cube e raised to minus 4s. You can express t cube e raised to minus st as some function, and you can do it as we have discussed before in the property. So that way it is very simple and very intuitive to understand. So let us talk about convolution. All right, so let us talk about some visualization. Okay, all right. Let us see some visualization of convolution in Laplace transform to understand how exactly it works. So now we know that the Laplace transform, basically if we take the multiplication of two functions and its Laplace transform, in turn we can say that it would be equivalent to the multiplication of the Laplace transform of the individual functions. So if say we are looking at two functions, maybe say e raised to minus at into e raised to minus bt, right? So what does that mean? So you take the Laplace transform of e raised to minus at and then e raised to minus bt, and then if you take the Laplace transform of e raised to at, or rather e raised to minus at into e raised to minus bt, what should be the product of that will be equal to the individual Laplace transform multiplication, right? So if you want to see the graph, right, it would look something like this. Now we know that e raised to minus at, what should be the f of s, e raised to minus bt, what should be the f of s, and we can then look at the multiplication, because a and b value we have set here. We have set a as 1, we have set b as 2. So accordingly, we are looking at the Laplace transform over here, right? So the first function e raised to minus at, it should look something like this. E raised to minus at and bt should look something like this. And if you look at the convolution process overall, it should look something like this, where if you see the convolution results, eventually it behaves something like this, right? And obviously it holds true. So likewise, you can change the combination. So maybe t sine t, right? And if we look at its multiplication, so we know how the individual Laplace transform should go, and this is how overall it should look, the convolution. Obviously we are seeing the overlap, right, in the area, and this particular graph perfectly shows the behavior of the convolution result as well, and obviously it holds true. We have verified it. So that way, I mean, you can see how the convolution visualizes. Let us for instance take delta t into u of t. Okay, so delta t obviously is an impulse function, u of t is a step function, and if you combine both of them, you should look something like this, and eventually the result should be a combination of both of them. You can see that overlap as well. Let me play it out. When we talk about convolution, say we have a function f1 t, its transform would be f1 of capital S, or rather capital F1 of S, and Laplace transform of f2t would be then f2s. And if I have to represent it graphically, it would imply something like this. So we can write it as x is equal to t is equal to x, t is equal to infinity, and x is equal to 0, representing the limits of these functions. And if you look at that, this is what the representation of convolution is, where we are trying to see what happens if we multiply the Laplace transform of two functions, or how we can represent it or map it, the product of the Laplace transform of two functions and the product of these two individual functions Laplace transform. That is the overall idea here, right? And in terms of mathematics, this is how we write it, right? The multiplication of the convolutions, and then in the integration, the cross section or the overlapping of the area, not the cross section, I would say, the overlapping of the area. That was not a word, in fact. So yeah, overlapping of the area. So if we now quickly revise all the formulae, so we know that if f of t is a e raised to at, the Laplace transform would be 1 upon s minus a. If it is t raised to n, the Laplace transform would be n factorial upon s raised to n plus 1. Sin at is a upon s square plus a square. Cos at is s upon s square plus a square, right? If it is sin at, we know that the Laplace transform is going to be a upon a square minus a square, and if it is cos at, it is going to be s upon a square minus a square. If we have a unit step function ut minus a, we know that the transformation is going to be e raised to minus as upon as, and if it is, say, a delta function, I mean a unit impulse function delta t minus a, it's going to be e raised to minus as. If it is e raised to bt sin at, then it is going to be something like this. And if we move on to e raised to bt cos at, it is going to be something like this: s minus b divided by s minus b square plus a square, right? If we talk about, say, t by 2a into sine 80, it is going to be something like this. And if we talk about t cos t, right, t into cos 80, it is going to be something like this. Now, let us talk about some more properties of Laplace transform, or revise, in fact. First is scaling. So if suppose we are talking about multiplication of a into t of the function, then simply all we have to do is divide a by s into the final Laplace transform, and overall divide the function or the output by a. And if we talk about the derivative, if we are taking the Laplace transform of a derivative, right, here we are going to see something like, if suppose we have dft by dt, we would write s into f of s minus f of 0. Now here small f of 0 indicates the substitution of the 0 value in the function, right? And if we talk about d2 ft upon dt square, the similar thing but expanded, right? And if we talk about this integration, Laplace transform of an integration, we can simply divide the Laplace transform capital F of s by s. Now, let us talk about the first shift theorem, or the first shifting, my bad. So if we talk about the first shifting, what we are basically going to do is multiply e raised to minus at by f of t, right? And the output is going to be capital f of s plus a. And if we talk about the multiplication of f of t with the unit step function t minus a, we simply see e raised to minus as into Laplacian transform of f of t plus a. Now, if we talk about, say, multiplication of t by f of t, we have seen that we simply take the derivative of the output, and if we multiply t raised to n, simply the nth derivative into minus 1 plus n, minus 1 raised to n, right? And if we talk about the f of t by t function, we simply take the integration. It is that simple. Now, what about convolution? So the idea of convolution, as we have already discussed, if we take the Laplace transform of the multiple of two functions, their output would be something like this. Let us, look at the same table. But if you look at the same table and switch the columns, like shift the columns like this, then it would become inverse Laplace transform. It is that simple. So one has to just, be able to understand this or appreciate this, and you're good to go. Say for instance, the Laplace transform of 1 was 1 by s. So if I ask you what is the inverse Laplace transform of 1 by s, you would get the function 1. It is that simple. So here this mere idea has to be incorporated. So if we want to say find the inverse Laplace transform of s upon s square plus a, or s square plus 9 in fact. So when you look at this intuitively, it should come to you. 9 is nothing but 3 square. So we should write it something like s upon a square plus 3 square. And when we look at s upon a square plus 3 square, it very much looks like s upon a square plus a square, which is nothing but cos 80. A is 3. So the output would be cos 3t. Right? And if we then look at, maybe the inverse Laplace transform of 2s minus 5, we would have 9s square minus 25 at the denominator, right? Eventually, if you look at it again, it should come to you that at the denominator, 25 is also 5 square and 9s square is 3s square. So somehow I need to relate both of them, the numerator and the denominator, so that I can, simplify them. Now, how can I do that? So first thing that I do is the inverse Laplace transform of 2s divided by 9s square minus 25 and 5 divided by 9s square minus 25. Why do I do that? I clearly see that relating 2s minus 5 and the denominator is a little challenging, so I split them clearly, and then what I do is I simplify the denominator. All right. So when I simplify the denominator, everything becomes very apparent. Now it's a simple case of trigonometric functions. So therefore, I go ahead and write 2 by 9 cos 5 by 3t and 1 by 3 cos 5 by 3, so 1 by 3 sine 5 by 3t. It is that simple. Now, one thing that you have to understand over here is the significance of inverse Laplace transform. So why do we need inverse Laplace transform when we have Laplace transform? So see, the eventuality of a Laplace transform, function, or say the action of taking the Laplace transform, is to solve the differential equation. So my idea is that I will start with the Laplace transform, meaning I will start with a function. I will multiply that function by e raised to minus st, take the integration, basically I take the Laplace transform, and once I take the Laplace transform, I get a function in terms of s. I simplify that. I then, take the inverse Laplace transform, and which eventually gives me the solution. So there would be some differential equations which would be rather typically very difficult to solve. Then what would I do is use this path of using Laplace transform to solve those differential equations. So the idea is to convert those differential equations to algebraic form by using Laplace transform, solving the algebraic form, and then taking the root back by using inverse Laplace transform. So this is the idea behind Laplace transform and inverse Laplace transform. I hope you are able to appreciate what I'm trying to say. Right. Now, say we are supposed to take the inverse Laplace transform of s into f of s. Right? So that would be simply d of dt f of t plus f of 0 into delta t. Right? Say we are supposed to find the inverse Laplace transform of f of s by s. It would be 0 to t, the inverse Laplace transform of f of s, right, dt. And we can then write 0 to t f of t dt. It is that simple. Right? So these things we have already seen, but we are now looking at it from a different way, from a different perspective. What about the first shifting theorem? What about the first shifting theorem? So if we look at the first shifting theorem, the inverse Laplace transform of f of s, right, of f of s could be written as f of t and inverse Laplace transform of f of s plus a. Then based on this information that we just have, can be written something like this. So this is a full circle moment for us here right now, and this is how we can use it. Obviously the theorem, the proof and everything is beyond the scope of this video. This video, you can treat it as a revision tool, not as a learning tool. Of course, we are therefore going very in a fast paced manner. Now if we look at the Laplace transform of e raised to at into f of t, the idea is cap f of s plus a, and if we look at the inverse Laplace transform of f of s plus a, we are getting e raised to minus at into Laplace inverse of f of s, right? So now let us talk about partial fractions. Let us talk about partial fraction method, which is going to be a very important tool for us. Now, why an example? Let me talk about it. So, say we have to find the inverse Laplace transform of s square 1 upon s square minus 5s plus 6. So, the first task in hand, because we don't have any function to describe this 1 upon s square minus 5s plus 6. So, the first task in hand would be to convert that by using partial fraction. So, what we do is we split it, or identify some way of splitting the denominator. In this case, it is simply 1 upon s minus 3 into 1 upon s minus 2, and this is what I do. I split them out. Right? And since they were of very simple nature, I could confidently split them out by making the denominator 1. That might not always be the case, but yes, in this case it beautifully worked out. So let us look at a different case. Say I am looking at a scenario where I have to find the inverse Laplace transform of s minus 1 divided by s square minus 6s plus 5. Now in this case, again, the denominator comes very intuitively to us. We can split it very easily, but what about the numerator? So for that, what I do is I first split the denominator and write it like this, right? So that I can then relate the primary variable of the denominator to the numerator and rearrange the terms so that I can write it something like this, right? And making s by s minus 3 as the variable, as the joint variable. So then I could then simplify it something like this. And when I look at it, it comes very easy to me that the first expression somehow is going to be related to a trigonometric term, so is going to be the second term based on the denominator. So I may then take the inverse Laplace transform of the overall function and simply write it as the inverse Laplace transform of first and second expression. And when I go out and do it, I'll directly write the final value. I should get e raised to 3t into cos 4t plus 1 by 2 e raised to 3t sin 4t. It is that simple. Now, there is an issue. The issue is if we look at an even complex denominator, something like this, how do we deal with it? Because we are looking at a denominator who has, or which has, the order of 4. So now we can represent it this way, because finding out the numerator is a little tedious task here, and we cannot just settle with a plus b plus c, because we have 4 fourth order denominator. We need to find out 4 variables in the numerator by using which we can map these 3 fractions really easily. And once we realize this, after that all the other steps becomes very easy. We split it this way. Now simply what we can do is start substituting individual values to s, making it 0 so that it goes away, and we can then equate it with the other 2 terms. So for instance, in this case, what I can do is I can start out by substituting a particular value of s. Say assume s is 0. So if s is 0, b into s becomes 0, s plus d into s becomes 0, a into s minus 1, so 0 into minus 1, that stays. So only a stays, and when I equate everything, a comes out to be minus 1. The similar exercise I carry out with the other variables. this is what we get. Now simply what we do is apply the inverse Laplace transform on all these functions. First, we know 1 by s is going to be simply 1. 1 by s minus 1 is going to be e raised to t, and accordingly we can find out the rest. Now let us look at the assignment questions. So we have s minus 4 divided by s minus 4 square plus 9, a very simple one for you to get some confidence. And then there we have s square minus 6s plus 7 divided by s square minus 4s plus 5 square. A little bit tedious, but yes, nothing that which you cannot do. You can easily do this, so don't worry. Now moving on, let us talk about the solution of differential equations, the primary usage of Laplace transform. So if we talk about ODE, right, and if we talk about a typical ODE where we have constant coefficients, where it is linear, right, and maybe let us start with the first order one. Okay, so we are supposed to find the general solution, the characteristic equation, and all those things for usually solving that ordinary differential equation. And sometimes it may so happen that we are not able to solve it, as I've already told it to you. So we can solve that by using Laplace transform. So let us look at this particular simple case. And in a typical case, since it is a second order equation, I would give out two initial conditions to you typically. Okay, so let us look at it. Now take the Laplace transform on both the sides. When you do that, the first term, we know what happens, it's a second order term, so the Laplace transform would be s square. Now I'm representing y bar by the Laplace transform of the function, so that should be clear to you. So s square y bar minus sy0 minus y dash 0 minus 4s y bar minus y0 plus 4y bar is equal to 64 by into 2 divided by square plus 4. And if you substitute the initial conditions here, because this is a nice time to do that, because you cannot move ahead without substituting them. When you substitute the initial conditions, this is what you get. And now this you can easily solve by using partial fractions. So we do that. When we do that, we simply get y bar is equal to 1 minus 1 by s minus 2 square minus 8 by s minus 2 plus 16 by s minus 2 square plus 8s by s square plus 4, right? And if we now go ahead and write down the final solutions after applying the inverse Laplace transform, this is what we get. Again, I've skipped a lot of steps, right? And the last step, there is no need to do any of these things. We can directly get the solution of differential equations by Laplace transform. First order, second order, doesn't matter. It's that simple, right? Now let us use Laplace transform, right, for say initial value problems. Let us write down d2y by dx square plus 2dy by dt plus 2y is equal to 5 sine 2t. Or maybe let us take t for the case of simplicity. Now we can simply represent it in this fashion, and the initial conditions have been given. You know the drill now. We'll apply the Laplace transform to individual terms. The first one we'll write down as a square y bar minus sy0 minus y dash 0 plus 2 s y bar minus y0 plus 2 y bar is equal to 5 into 1 upon s square plus 1. Obviously sine t, alpha is 1, so we can write it this way. And now we can substitute the initial conditions. This is a good time to do that. So when we do that, when I substitute all the initial conditions, this is what I should get: s square y bar plus 2sy bar plus 2y bar is equal to 5 divided by s square plus 1, right? And let us now look at what happens when we solve this. Now this calls for the need to do partial fractions. So let us do it. Y bar is equal to 2s plus 3 divided by s square plus 2s plus 2 and minus 2s plus 1 divided by s square plus 1. Again, it may not come to you directly. Take your time, have a look. It will come to you once you practice a couple of problems. So I take the inverse Laplace transform of both the terms. Right? And this is what I should get. I know when I look at the first term that s square plus 2s plus 2, I can simply convert it to s square plus 2s plus 1 and then take s plus 1 bracket square. So that I use, and at the second term, when I look, it is very clear and I just need to split it. So I split it because nothing can be done about the numerator. So when I do that, everything becomes very simple. Something like this, yes, and I'll do the similar action there. So if I write y is equal to 2 e raised to minus t cos t plus e raised to minus t sin t minus 2 cos t plus sin t. This is what it becomes. Now, at surface, it may look difficult, but as you have seen, it's all the steps were very simple, right? So if I have to summarize you the steps of solving the Laplace transform equations, or of solving the Laplace transform of differential equations, the first step would be you applying the Laplace transform on the individual differential terms, getting the resultant equation, substituting the initial conditions, then simplifying everything, making sure that the transformed variable, meaning f of s, or rather in this case I would say y bar, or say Laplace transform of f of t, goes to the left side and everything else comes to the right side, the algebraic equation in terms of s. Then by using partial fraction method, you will further simplify it, get it to a form where you know now the individual inverse Laplace transform formulae, and then you can apply those to get to the general function. I hope you understand this algorithm now. So now please solve at least these two problems and comment their answers in the comment box. I would really appreciate it. Now, some more examples on convolution before I wrap this video. I would want you to also follow this with me. So say for instance we want to calculate or find out the convolution, right, for say inverse Laplace transform, to find the inverse Laplace transform, right, of f of s, then I would write or look at this particular function, right. Now we would want to simplify this in a way where we can use a convolution. So here it turns out these two are the function whose convolution I need to find. Now what I do is then I represent this particular thing in such a way that I am able to get some recognizable form, right, some recognizable form, so that I can then assign them to the individual functions. So f of t, and then sorry, f of s, and then g of s. So see, this is the output, this is the going to be the output. So since we have already used f of s, so I have now converted them to a recognizable function or recognizable form which can be worked on, which is actionable. Because see, the Laplace transform of t raised to n we know n factorial upon s raised to n plus 1. The Laplace transform of sin at we know a upon s square minus a square. So now f of s, if you look, root 3 by 2, the Laplace transform of t square, it's simply going to be that. And then the Laplace transform of sin, root 3t. It is that simple, right? So eventually when you start looking at the functions, start looking at the solutions, right? See how they fit together. Things will start coming to you very generically, very naturally. Now, we know how convolutions work. So I can simply multiply t square by sine root 3 t, and I am good to go. Okay, and finally, before we conclude, I would like to also add one point, because this is a very common problem or a common application that is discussed apart from the mechanic, the spring mass dampener system as well. Uh, these are all just a simple way of writing those equations, or another way of writing those equations. So instead of being given directly the equation of, say, a mass spring dampener system or say an LCR circuit, right? They are giving you the entire problem statement and want you to construct that equation. So for that, let us look at this simple case. So say if we have a condenser, it is of capacity C, it is charged to a potential capital E and discharged at t is equal to 0 through an inductance which is L and say a resistance which is R. So the charge Q at time t, what would be the differential equation? If I write down the differential equation, you would say that it's a simple differential equation. But when I write the problem statement, after reading all those things, you may get a little overwhelmed. So you have to take a step back, look at the problem very objectively, and come back and look at the differential equation, or rather, even memorize the differential equation, and it will come to you automatically. Just look at the differential equation. It's so simple, right? We have solved, the different forms of it, and you can also do it very easily. So, overall, to wrap it up, in this video, or in the earlier video and this video, in these two parts, I've talked about Laplace transform. I have given you a brief overview of its various properties, its various aspects, the Laplace transform formulae, its various things like unit step sequence, unit impulse, and things like convolution and all those things. So I hope I was able to at least give you a brief overview of Laplace transform. Obviously, this both these videos were not meant to teach you Laplace transform, but help you revise the concepts or give you a brief overview if you don't know anything about it, and then from here you onwards you can start. So I hope I was able to do that. Thank you for watching. Have a great day.